Welcome to our lectures on fax devices. We were continuing with the control of the PQ techniques control. These are some discussion is left. Thereafter, we shall discuss about the comparison of the UPQC with the power angle regulator. First, we will take out that control of free flow power control. So, we were discussing basically the basic control system of the PQ control in our previous lectures. So, this is V1 and V2 def. Essentially, this is a sag controller. So, we have to check it out if there is a sag or not, or sag or swell, but most of the cases the problem arises from the sag. So, you have a power amplifier, and from there actually you will compute that what is basically the SHQ limit. So, that is a shunt compensation limit, and thus from the error amplifier PI controller you will get an alpha. And again, so from the PLL you will generate theta. So, you will sense the actual ISH that you are trying to inject, and you will have a limiting computer, because if it is very high it should restrict it, and that will be subtracted from the ISHQ, and with this subtraction I alpha will be generated, and it will be fed to the get signals of the shunt converter, and with the desired theta coming from the phase lock loop. So, in that way actually we will maintain the voltage sag compensation. So, this is a functional block of the shunt converter control for operating varying DC link voltage. There we are not actually maintaining the fixed DC link voltage as discussed in the previous class. So, here actually you have to sense, and from the sag we will be maintaining the DC link voltage. In the control scheme of the shunt converter shown in the previous slides, with variable DC voltage, the magnitude of the output voltage is directly proportional to the DC link voltage, and only its angle is controllable. So, there is a change in mechanism of these two. With this control scheme, the DC voltage capacitor is changed by momentarily the angle adjustment, and thus forces converter to change the real power. So, the actually instead of maintaining the DC bus voltage and a control loop, we basically change the phase angle, and thus we change the power actually passing through it, power with the AC system to meet the shunt reactive compensation requirement. Now, let us come to the point. We have seen that the previous discussions that this UPFC can work as a shunt, as a actually power angle regulator in case of this actually in previous slide, where actually voltage is not maintained, DC voltage is not maintained and it is fixed. Why then we, of course, that comparison comes, why can't that UPQC will be actually used as a power angle regulator? So, what is the scope of UPQC of using as a power angle regulation, and where is its advantage and the disadvantages? So, UPQ, it is introduction to the UPQC as PAR and its comparison. That is what we have shown, because 2-3 slides were remaining in previous discussion. So, we are fitting it here. In objective of this section is to compare the character of the character of compensation attainable with the series compensator, phase angle regulator, and the UPFC for power flow control. Consider once more the simple two machines analysis. We shall have a actually sending end voltage, thereafter actually X we have a receiving end voltage. This is V angle delta and V angle 0. This model can be used to establish the basic transmission characteristics of the control series compensator. These are, we have discussed thoroughly, TSSC, GCSC, TSC and SSSC. SSSC definitely is the superior among the other passive component. And the controlled phase angle regulator, that is thyristors controlled phase angle regulator, or the SVS best by using the and now by using in place of the UPFC. So, what will be the changes here? The ideal phase angle regulator provide voltage injection in series in the line, so that the voltage applied at the input terminal appears same with the magnitude, but delay or leading, but with a plus minus sigma phase difference with the output terminal. The synchronous voltage source or SVS based phase angle regulator have a power circuit structures similar to the UPFC and can provide an angle control without changing the magnitude of the system voltage. The purpose of the present investigation is to compare the power flow control capability of the UPFC, so that the phase angle regulator, it can behave as a phase angle regulator. And for this comparison, the practical implementation of the phase angle regulator and its ability to generate reactive power is unimportant. So, we shall only see that whether it can give a desired phase shift or not, whether it can control the PQ which we have seen. That is not actually domain of considering the utility of PAR. Thus, what happened, for the simplicity, both thyristors controlled and the SVS based PAR is considered as ideal phase angle regulator. That is, both assume to be able to vary the phase angle between the voltages at the two ends of the insertion transformer in the control range of plus minus sigma. So, maximum sigma max to minus sigma max without changing the magnitude of the phase shifted voltage from the original line voltage. So, it will just will have a V here and somewhere you got a PR, here it will change delta to plus minus sigma and so on. That will be the case. Consider the two machine system as shown again in the PAR, we have done there in case discussing PAR, to functions as a ideal phase angle regulator. The transmitted power and the reactive power demand at the sending end and the receiving end can be compensated system, that is V square by x sin delta, and uncompensated line is V square by x sin delta. Similarly, PS equal similarly QR equal to QS equal to V square by x 1 minus cos delta, and where it will be actually changed now by this new delta, that is delta plus minus sigma. So, this is the case of the comparison of the UPQC to PAR. So, now this is the phase angle regulator. So, it will take some amount of power from here and it will inject the V sigma, so that actually effective voltage source become Vs plus V sigma, and thus DL power flow changes. So, previously this was the value of the Vs and this was the value of the VR and this was the angle. Now, with the injection of V sigma, it can be either of it in a, so that actually the magnitude of this value of Vs effectively remains same. So, this became the new value of V effective or this value of the V effective. So, what happened then, and accordingly sigma changes, and thus this becomes your new delta. So, in that way this will operate, and this becomes your new voltage across this actually the inductor. Thus, what happened, PAR cannot increase the maximum transmittable power. It is restricted to V square by x, it will be V square by x. Only it can actually change the point occurring the maximum. It can make it the maximum power at 30 degree, 60 degree, even at 120 degree, but we do not operate at 120, or change Q at fixed P. So, it is not possible. Function of the PAR is simplest to establish the actual transmission line angle delta required for transmission of the desired power. Let us say P required to be 0.7 and you have V square by x, this value to be 1 and sin delta, and this delta can be anything when you can add a rho or sigma to it. So, you have a wide range of flow of power and you can deliver with this independent, almost independent of the delta, you can set your desired value of the power. That is what it is saying. Adjusting the phase shift angle sigma, so that to satisfy the equation that sigma bar equal to sigma minus sigma delta bar equal to delta minus sigma is given by delta is prevailing angle between the sending end and the receiving end voltages. The PAR can vary the transmitted power at fixed delta or maintain actual transmission angle delta constant in the face of varying delta, but it cannot increase the maximum transmittable power or control the reactive power flow independently of the real power. The QR and minus P relationship for the ideal PAR in comparison with that UPFC at delta equal to 30 and delta equal to 60 and delta equal to 90 is been shown here. So, this is the controllable UPFC with PAR and this is a limit with a V sigma, and this is the uncompensated one, and similarly this is a controllable region. So, you can deliver up to 0.5 and you can change the delta accordingly to any point. This is with the power angle regulator. But in case of this, in case of delta equal to 30 degree, so thus there is not much change of PAR for and the PAR and the UPFC at delta equal to 0, they are same. But in case of the 30 degree, this is actually the Q max and what you can inject, and thus you can see that this is basically the controllable area of UPQC whole area, and this is the area of PAR. So, here it will intersect. So, at this point PAR and the UPFC will have a same kind of compensation, but PAR can compensate in this curve and UPQC has a versatility, and moreover, so it can compensate in this region as well as the upper region. So, definitely for higher angle, soon the angle is increasing, the compensation of the PAR will decrease because it is closing near to the 90. So, ultimately it is delivering the maximum power. So, no point of having any phase shift in a PAR. Okay, we shall see to the next slide. This is for 30 degree. So, power handling capability of the PAR will be inferior, only it is same for delta equal to 0. So, now this is a case, now the origin will shift because delta is at 60 degree, delta equal to 60 degree, then when the real power becomes 0.866. So, this is the 0.866 and 1 minus cos delta will accordingly come. So, then that will be the value. So, this is the case of the origin and you have a point of intersection. You consider that actually value of VQ is 0.5. So, V square, so ultimately this value is basically 0.5 per unit. So, you have a circle of radius of 0.5 per unit, and ultimately this is the range of the PR and this is the range of the PQ of this actually the UPFC. So, UPFC can make it 1, definitely it cannot go beyond 1. So, it can compensate in this line PR, but UPFC can send power within this circle any point. So, maximum power handling capability even at the 60 degree it is same, but it has a more versatility. It can compensate power this point, this point, this point, this point, but PAR has to go through only this line. This is a P and Q line. Now, let us consider when it is 90 degree. It is already at its maximum position. So, origin will be center will be at the 0.11. PAR can reduce the power, not increase the power. So, PAR can act in between this region depending on the maximum value of the sigma, but here you can go to make the power of 1.5 in case of the UPFC. So, you can have a more transmutable power in case of the UPFC when delta is more. So, thus UPFC is a suitable and advantageous solution than the PAR. So, what are the takeaway from these discussions? This UPQC versus P plot clearly shows the superiority of the UPFC over the PAR. UPFC has a wider range of real power control and facilitates the independent control of the receiving end reactive power demand over a broad range. As discussed, thyristor switch capacitor, that is TSSC, and the gate control series capacitor, that is basically mostly it is GTO based GCSC schemes employed under the capacitor bank in series with the line is thyristors or a GTO to bypass the switch. So, what happened then? This arrangement is effective to equivalent to a series capacitor whose capacitance is adjustable and in steps like the continuous manner. So, you have a capacitor and you have a switches. So, this can be switch can be once it is triggered fully, then this capacitor is got bypassed. We have discussed in case of the series compensation in detail. controllable series capacitor impedance provided by the TSSC and GSSC cancels part of the reactive line impedance, resulting reduced overall transmission line impedance. So, value of the X got reduced. So, there is a different kind of problem we have discussed while discussing the series compensation. For this purpose, the present investigations, both TSSC and GCSC, can be considered simply as a continuously variable capacitor whose impedance is controllable within a range of 0 to X0 to SC max. So, you can, when it is fully switched, so capacitor is bypassed, so it is 0, and accordingly when you control the switching of this thyristors and you got a control over the capacitors. So, what will be the comparisons with that? Series definitely can increase the power flow. The static synchronous series compensator injects a continuously variable series compensating voltage is quadrature with the line current, in contrast to the TSSC and GCSC. The compensating voltage of the SSSC, that is the series compensator again, can be controlled totally independent of the line current. That is one of the biggest advantage of the SSSC over other kind of series compensation. With suitably designed thyristor control reactor can be used for the inductive compensation also. We have seen that TCR can be also inserted into the system. Inductive compensation range for practical reasons are usually less than the capacitive range, because most of the energy is consumed in drives and these are inductive. For this purpose, the intent of comparison an ideal TCSC with a sufficient number of constituent module, we assume that. So, we have seen that huge number of TCR capacitive compensation and only one actually inductive compensation. Such TCSC is capable of providing the equal capacitive and the inductive compensations and able to continuously control and maintain the compensating voltage in the phase of the decreasing line current. With assumption that TCSC can be considered as SSSC until the transmission line angle becomes much small to maintain the sufficient line current needed to normal operation. In ideal, TCSC is probably beyond the economic practicality, but simulations does not significantly affect the present comparison. So, control series compensations provided a series compensation voltage that by definition is in quadrature with the line current. So, but what is the difference of the UPFC? So, it can be in any phase. It can affect only magnitude of the current flowing through the transmission line. So, that is something that it can control. At any given setting, the capacitive impedance of the TSSC and GCSC are particular overall transmission lines impedance is defined, at which the transmitted power is strictly determined by the transmission angle. Therefore, reactive power demand at the end point of the line is determined by transmitted real power in the same way as if the line was uncompensated, but had a lower line impedance. So, we can assume that with the compensation it looks like actually X is modified by the X reduced. So, it can take it a uncompensated power. Consequently, the relationship between the transmitted power and the reactive power demand of the receiving end QR is represented by the single circular loci of the PQ circle, we shall see right now. For continuously compensative controllable compensations, an infinite number of QR and the PR circular loci can be established by using the basic transmission relationship, that is P equal to V square by x minus xq sin delta. Similarly, it will be V square by x minus xq, the inserted impedance, it can be plus minus ideally, and into 1 minus cos delta, with q varying between 0 to plus minus q max. So, where xq equal to xe for the TSSC and for the GCSC, and it will be Pq by I for SSSC. Thus, the QR locus representing the power transmission with maximum capacitive impedance compensation is the upper boundary curve of the TSSC and GCSC, and it is identified by QR P max. The lower and the upper boundary curves of the SSSC, TCSC is considered are different from TSSC and GCSC, because these are shunt compensation, these are basically the passive compensation, and this is basically the active compensation. Therefore, they are identified by QR minus P plus minus max to this max. So, it can have a both the range. The difference is partially due to the capability of SSC and TCSC to inject the compensating voltage both with 90-degree lagging or 90-degree leading relationship with respect to the line current. Thus, we can increase and decrease both the transmitted power by the series compensation. For this reason, the SSSC and TCSC have a considerable wider control range at lower transmission angle than the TSSC and GCSC. The QRP circular curves are considered only for the normal operating region of the transmission line, and where theoretically it should be 0 to 90 degree. The plot shown below at 4th transmission angle, delta equal to 0, delta equal to 30 and delta equal to 90, same we have done in case of the PAR. We are going to repeat the same thing with this actually series compensation for TSSC, GCSC and TCSC and SSSC with the same maximum power rating as stipulated by the UPFC. So, we should have a apple to apple comparison. Each figure of the upper and the lower boundary curves is defined above. For the TSSC, GCSC, SSSC and TCSC are shown by the dotted and the broken line. So, this is something you will see. This is the circle, essentially the control area of UPFC, and this is basically Q max, thus this is the control area of SSSC. So, this is for angle delta, and you can inject current, you can take it to any point, and thus you can see that ultimately it is crossing at this point, and this is the line for xq equal to 0, and you can add and decrease the xq, and thus you can increase the power of the system. So, we can see that at a lower angle maximum compensation you can make through UPFC is 0.5, but you can make it in a higher value with the help of the series compensation. Now, let us consider the case when delta equal to 30 degree. So, origin will shift P at 0.5 and Q1 minus delta, it will be 0.18. So, you are at this origin, and this is this circle is the locus of compensation of the UPFC. Now, this is the line for Q equal to 0, and it will pass through the origin, and the way actually you change the delta. Now, this is the IQ max. So, you can see that at this point you can have this much of extra power for this much of extra power for for this reactance compensations, that is for TCSC and all, and this much of extra power handling capability for actually triple SC. So, triple SC will be actually much superior, and we have this much to this much power handling capability by TCSC. Now, see that when it is 60 degree. So, now there it will be same of this is the line of the maximum C max, this is the line for uncompensated XQ, and this is the line for VQ, and ultimately this much of extra power you will get it, and here we cannot claim superiority. Here also actually superior is the UPQC, because you can inject any power in between this circle by the UPFC, and ultimately if you are operating here as uncompensated line, if you use the passive series compensation, you can go to this point, and if you use the active series compensation, you can go to this point. So, within the range of this actually the boundary of the cycle only, but when it is changes to 60 degree. So, you can see that both this curve is meeting at this point. So, as far as power handling capability is concerned, both this VQ and the XSSC, that is active series compensations, and the passive series compensation does not have much change. So, it is operating at the same point, but power handling capability of these three devices are almost same. So, it can handle this amount of power. This is for both the three cases. Now, for that, when actually it is 90, here there is a clear cut advantage. This is uncompensated line, and this is a line for XQ, and this is the line for the XB. Now, you can see that this line splits, and ultimately the passive solution will have a superiority, and it can go to this point. So, only for angle at 90, we generally never operate at angle 90 theoretically. So, we will have a passive solution, we will have more advantage than the active series solution, and zone of control it is less in case of the UPFC than the series solution. So, these are the discussions. So, these are the takeaways from this figure. It can be controlled that the UPFC has the superior power flow characteristics compared to the passive. These are passive series compensator, and this is one is the active series compensator. It can control independently both real and the active power over a broad range. If that circle of influence is taken as 0.5, you can increase it to 0.6, 0.7, but rating will be increasing. Its control range in terms of the actual real and the reactive power is independent of the transmission line angle. So, it does not touch the transmission line angle, and it does not touch other parameter, and it control both real and the reactive power flow either direction, that is at 0 to the small transmission line angle also. So, thank you for your attention. That is all about our comparison with the UPFC with power angle regulator and the series regulator. So, what we can conclude here, that power angle that all the cases, the activity of the power angle regulator and the series angle regulator, that all the activity we require, that can be effectively and more efficiently possible to do with the UPFC, and thus UPFC is a future trend and it will replace the other kind of series compensations. And once if you have a virgin location, that is you have not really not fixed any kind of the fax devices, of course we will prefer UPQC instead of this different kind of series and power angle regulator. Thank you for your attention.